So we do spectroscopy, and we do the quantification of the yields, and I want to open that in Colab. I want to run it anyway. And we need to open a file in the hygroscopy ecosystem. We have different parts. So this one is mostly for scanning probe microscopy, atom AI, the old atom finding one, and we have the sci-fi readers. And I use those sci-fi readers for opening all my files. So if you have come across a microscopy file that you cannot read, contact us and we'll check whether we can read that. So most SEM, TEM, and scanning probe microscopy file systems can be read with that. And so now while I bridge that, we are done. We have to restart our runtime. Oh, okay, we don't need to restart it. Yeah, it's this one. Okay, here we have to restart the runtime. I have a few of them open. Restart session. Everything stays here. And we can open that now. The reason we need that is, as I said, we want to zoom in and out of spectra and images. So if it's not interactive, for me, it is not really worthwhile doing. Well, let's connect to my Google Drive. That's the fun thing about that. So if you have it on your Google Drive, you can directly add your own data. You don't need that. Okay. What's going on here? So what we do is we are in Google Colab. So what I did is I downloaded an ENB file to this folder, and it opens the file widget. And the reason I use file widgets is so that we can use it on Google Colab or any other system. You don't have to have an open file window. So we select that as main. Takes a little while. So you see we have a Super X system. And the first thing we want to do is we want to look at that. And this is the spectrum that we are having. It's the first thing in a spectrum that you want to know is how noisy is it, right? So you just go here and do that. Okay. I, for some reason, have to run it twice. Something is not holding up, or maybe I have to do it again in a moment. So my background wasn't really quite well. So the next thing, we have a spectrum, and we want to detect what elements are in there. And all systems do that. And of course, I do it differently. But we can see, if we zoom in, these are the strontium edges, right? As the strontium peaks, we have two overlapping ones here, and we have one here. we have a nice mess in the lower energies, right? So we have a copper L edge, we have titanium here, and so the way I'm doing that is a little bit different. So I look at the strongest peak first. So which one is the strongest peak? I have to go back to this one. Strongest peak is this one. Okay. That is strontium. I determine this is strontium, it's a strong peak, it has to be a very strong line. So it's almost unambiguously strontium, so it's no much things you do. And then I say, okay, if this is strontium, what other lines do I expect of strontium in my energy range? And I subtract that. Okay. Then the next thing to do is I do that again with whatever is left over, the next strongest peak. And titanium I haven't subtracted, so it's still there, right? So I subtract all the titanium peaks, however large they are. And then I move along. Oh, this is also titanium, so that's already gone. So I wouldn't work on that one anymore. And then the last one is the copper one and the oxygen one. Oh, we have oxygen. I forgot the oxygen one. So the oxygen peak is here, actually not titanium. So it's oxygen, and then I do the titanium later. So that way, you can even overlapping edges would not obscure your positioning. A lot of softwares find fluoride in your spectra. With that method, you don't find it because it is one of the low-lying edges of copper that is not used normally. So anyway, it's relatively robust. If it doesn't work, you can always add some kind of materials. And so you can try that. And it depends on how many peaks you're finding in that. That can be a little bit better refined, no question, right? And what we do then is, can't look. We fit the background, and the background is the Bremsstrahlung convoluted with our detector. And I fit the families of peaks. So I have a K family, K alpha, K beta, K alpha 1, K alpha 2, K beta, whatever we had before, right? So I have the K alpha, it's the first one. And then I know the relative intensity of the next ones. And I fit the whole family of peaks to the spectrum instead of only a small peak or a single peak, right? The different methods of sophistication. The simplest one is when you try to determine the peak intensity is just to look at the background left and right. And then you subtract a linear, because you know your background is rather benign, you subtract the linear interpolation between that, and you just sum the counts where this peak should be. For overlapping peaks, you're out of luck, right? So it doesn't work. While this method does still work. Also, you have to watch very, very carefully in the program where it places exactly the background fitting for the background extrapolation. If there's a peak in there, then suddenly you have a background that goes up. One of the biggest sources of user errors in EDS analysis is not watching how the background is extrapolated. You have the same problems, I guess, right? So people are not checking that. So you have to check which background subtraction you use and what the errors are in that kind of point. So that is the simplest one. Others fit a peek into it. That's a little bit better because it requires a flat background. And as I said, I fit my background on there. Let's see how good the fit is. We'll zoom in a little bit. You notice that I do not do anything with my peaks. I look up the position of them. I calculate what the width should be. And that's it. And I fit the only thing that I'm fitting is actually the height of the whole family of peaks. So the peak, so I know exactly how, so this one is strontium K, I guess. So I fit this peak here and this peak here. And I do not change the relative height of these peaks. And you see it, I don't have to because it works, right? So both of them, the whole family here works. There are a few smaller ones along the line, but they are probably too small to be seen, but they would be taken out as well. The position is not accurate. We see that because we have a kind of differential signal here. So my energy scale is not exact, but if you look at the error, it cancels out, right? The nice thing now is I can actually look at my noise level in the system unambiguously, right? So we can see exactly where it is supposed to be. And the high-lying edges, as we have them here, as you see, so that is titanium, works very nicely. The key factor, however, is how does the background work at the low-lying edges, because that's really where the biggest problems are with the background. And that depends now how well do you really know your detector. And in this case, it is actually reasonable. Again, we have a very small error here. Maybe that's not what I want to do. It's a bit too much, right? Let's go back. So I want maybe more like this. So the background error is relatively small. Could be that there's some ice buildup on the detector, or I just say it kind of gets screwed up by this small peak here, right? So any of these things would change that. The main thing is at small energies, the energy scale calibration is off. If I would, and I was refrained, that's something I wanted to do, but I thought I don't do that before the summer school, is to just, let's say, peaks move a little bit left and right, so that we might be even able to scale the energy with that. But the key thing is the only free parameter is for each family the height, and the height of the background, so the amount of Bremsstrahlung that I have. That is it. So I really limited the amount of parameters here, and the fitting parameters for each family is directly my quantification. So I don't have to do anything else on that. And I get even an error because I can just subtract the two things. And I know for each single family, what is the possible error in my quantification. Because I have a model, and that is the key thing in the model is that you're not only getting your quantification, you get your error because you can subtract the model from the spectrum. Okay. And now we quantify the spectrum, and I use the so-called K-factor. Okay, I think I have to do from the EM tables. So the EM tables comes from the group of Cécile Hébert from EPF, so that would be in France, Switzerland, not France, but they speak French. And then if we quantify that with a standardless, with calculated K-factors. The K-factors, okay, now I realize that I have not introduce the K-factors, which we will do in a moment. So the K-factors give us the relative counts of an element with respect to a reference one. In our case, it is silicon, I think. Others have the relative as a reference iron. So there are two different schools of references, but you can see that very easily, whereas at whichever element the K-factor is 1.0, that is your reference, right? So you have one with 1.0 and you're done. So the tabulated ones, let's see how accurate it is. This is strontium titanate, right? One strontium, one titanium atom, and 3 oxygens. So I have 5 atoms in my unit cell or in my compound. So I should have 20% strontium. That looks good. I should have 60% oxygen. That does not look good. So we are off by quite a bit. And we should have 20% titanium. So the standardless K-factors are reasonably off. And that are still, I think, the best ones that are directly calculated from the cross-sections that we can achieve. We can look up their papers. I saw they have. Okay. You can look at, if you look at that link from the EM tables, they have a paper on that. They explain exactly what they're all taking care of. And it's as much as you can do, actually, I think. So they do a very good job of that. And so that are probably the best ones that are standardless. The EDS spectrometer manufacturers, or the ones they, at least the ones that sell it, they make actually quite some modification to these K-factors, and they calibrate them on, because they know their spectrometers, and so they can tweak these K-factors some. And so the K-factors from our microscope, if I use that, I have them here for oxygen, titanium, copper. If you need to know how to get that out of your microscope, so you can Google that. It's out on the web. I'm not going to tell you that. And so if we do that, it looks already much better, right? Because the strontium and titanium, strontium is a very high energy, right? Titanium much lower. So you can see that is actually a good test case here. And both of them come out with about 22 atom percent. And oxygen with 55. Now, if you have a quantification like that, the experienced EDS person says one thing immediately. Now, you guys. Huh? No. It's not real. That's the point, right? It's absorption. Which photons? So I'm sorry, I didn't want to. There are many different reasons why it could be, but if we know, of course, that we didn't destroy the system, the crystal here, because we distributed the dose. We wanted to have a reference in it, spectrum. But yeah, it's often that we just leave it a single beam there, right, and the oxygen goes out. That could be one thing. But let's assume it is we didn't destroy the sample while doing that. So it is the low-lying edges with the photons that have low energy. If you want to get them out of your sample, you have absorption. And the same way that I did actually cheat a little bit. When I fit the spectrum, what I do is I calculate the spectrum with the full Bremsstrahlung, and then I convolute that with the detector system. And so what I do now is I convolute this spectrum with whatever I had over here in this quantification. So I say, okay, I have that and that many titaniums, that and that many oxygens, and strontium, and they act for me because they are in front between the source of the photon generation and my detector. They act for me like a window. And so I convolute that on top of it, the whole spectrum. And it will increase the small ones and decrease the higher ones in a relative point. And let's be adventurous, right? I mean, it was not such a sick sample, but we could have used it. And then we see what the correction is. And you see it's exactly happening what I said. So the oxygen would be signal or analysis would be corrected upwards, and the higher lying one would be corrected down. In principle, if you know that you didn't screw up your sample, you can now go and try to find where do you have about the correct quantification. It's around 80 nanometer. And you see we are plus minus 1 atom percent correct in the titanium, strontium, and oxygen. So how accurate is this thickness measurement? It cannot be super accurate, right? So let's do 70%. That would 70 nanometer. That would also work, right? So give or take 20 nanometers. So it gets you in the order of magnitude for your thickness, because that is the remaining uncertainty in the quantification. But if you want to quantify something more Yeah, I know 70 nanometer looks better, but where do you trust it, right? So 0.5 up and down, that's where I would put it too. That's correct. After absorption, exactly. But I want to caution you, so it really should be done iteratively. And before you trust it too much, you really, really have to check your fit, because that is really where we are basing everything on. So let's look back into my fit and see, okay, there's plus minus. So my fit is actually quite nice and good, and I can trust it relatively well. So again, the quantification is quite clear. The cool thing is, in a TEM, we are usually trying to quantify things that are very close together. So we usually can assume that our absorption is the same. So the sensitivity to small changes in the composition is much better than the sensitivity to than the absolute quantification, right? So if I see that the titanium, let's say, goes down within a few nanometer, then this defect grain boundary interface is titanium deficient, except if it's right next to something heavy. Let's say I put that strontium titanate on a big block of platinum, then the titanium might get absorbed. So I have to check these kind of things. But generally speaking, with the same points, I have very, very nice quantification. We had some questions in the chat here. Let me check. Yours is more screwed up. Okay. I would, if yours is more screwed up, go back here. I had this problem. I'm not sure where this bug is. So I was alerting it. And glad you're doing that. If you do this code cell again, where we do the detector efficiency, and then if you look at your fit, for some reason, the oxygen doesn't get fit because the fit region is somehow screwed up. So I'm not sure where that happens, and I'm not sure why it doesn't take it every time. I have to look into that. But we have to look at the goodness of the fit, and if that didn't work, then most likely that is the problem. See here, this small titanium peak? I did not fit that by itself. I only fitted all of the titanium peaks. So I just wanted to make you aware of it. And there is actually another titanium peak down here, so which is also taken care of in that part. So what that fit is giving us is overlapping peaks are not a problem, because I'm not fitting a single peak. I fit the whole family. And there might be one peak overlapping, but not the whole family directly on top of each other. That does never happen, right? At least it didn't come across to me yet. So that's odd. 25, 26. Yeah, I think that is an excluded kappa. Yeah. We did not have correction. That is correct, because ZAF stands for C is of course the relative composition. So we do that. We absorption. We do absorption here. In this case, down here, right? So here we do our absorption correction. This is our absorption. That's the A of that. And we do not do fluorescence, because our samples are small enough. So we had this discussion in the last lecture. Still not fitting this page. Double check your oxygen peak, whether it's fitted correctly. $49. Yeah, that is exactly what I got with did you load my quantification dictionary? Because this is exactly what we get here when we do without the quantification dictionary. If it does not find the quantification dictionary, the program automatically falls back to the EM tables k-vectors, and that, as I said, are as good as it gets, doing it all from scratch. So try this one here, the next one. Yeah, that is exactly the point I was making. So 0 up to 680. So if you run this code cell a second time, then it should work. Shantanu. I know it's a bug, and I didn't find the reason for it. Spent my whole breakfast with that, so it needs some illumination and more digging into that. Okay. Do we have any other problems? Any questions on that? Okay.
So on the Velox software, it also have like a density correction. So how does it, do you know, like how does density affecting the EDS, or it's
how what detecting?
Density.
The density. Density of your sample. Okay. Yeah, in the Velox software, if we go back there, oops, I unconnected. Oh no, that's wrong. Oh, I didn't close it. Drilled a nice hole, I guess. Anyway, thanks for getting me there. Let's look at this monitor too. It's this software here. Now, actually, we have to do in the analysis. We stop this. We have to view monitor 3, I guess. Okay. And I have this in my way. Okay. There is actually a sample thickness and density, right? So do the same absorption correction I do. So you just calculate, called trigonometry, right? So we are very well versed now in trigonometry from diffraction. The beam comes down, it goes to the detector. So you get this, you have to get that angle to calculate this length, and you need to have the thickness, and it assumes you can put in a thickness here, and then it will calculate it for you. So it's the same absorption that we do there. And I got my K factors from their software. So if you do the analysis here, and you save your spectrum, they will tell you what K factors they used, and you can just use it directly as well for any other analysis. So the K factors, as I said, are modified and tweaked to use. They work very well for the K edges, and L, M, and so on are bit more dodgy. If you're looking into comparing the K, do the same thing of the K vector with strontium L instead of strontium K, you will find a large deviation from that. Let me see, do I have? Okay, I'm not sure what the problem is. Good. So so they are moving the energy axis around to do stuff, and there is a way. So the brown power one are the ones that are a bit optimized here, so that is proprietary. What is about is the one for the cross sections themselves, and that is what EM tables uses for their cross section quantification. So that one, and the background correction, it does the background windows automatically, and so that is something you have to watch out for. It's not my software, so I'm not going too much into that. Okay, so but all of these softwares do have the same capabilities, right? Because we need that from a physical point of view. Okay, the K vectors. So if I go to this is not the one I want to change. Go to the Jupyter book of that. I had a section here on. I have this example here in my lecture. It's a SEM image. It's one of these mystery things, right? So you get an image, there is a very bright dot there and some other ones. And I can guarantee you that you do not guess what it is. Even so, all of you have seen it and eaten it, I'm 100% sure. First clue, okay. It's eaten. And then if we analyze that, where is the, find the maxima, blah, blah, blah. So we do that step by step here. Find the peaks. Here's the peaks. So we have phosphorus, carbon, oxygen, magnesium, and potassium. Huh?
Banana.
Nah, good guess. But the point is, I should point out that the potassium and the magnesium is only in the bright one. Carbon, oxygen is in the other one. This is chocolate. Huh? Is it guessed in the chat? Chocolate. Good. Okay, we have a chocolate affinado. So who would have guessed? Okay, so nothing too bad for the students of Tennessee. That is organic, 90% chocolate, right? And it was put into the SEM because nobody wanted to go up to 90% to do some other tests with them, like melting them in the mouth and stuff. So we did some chocolate testing, including laser processing and compression testing and all that stuff. So we had, at some point, we changed our curriculum and we hadn't had a course for the undergraduate students. So everybody got somebody and they had to do, got a material and had to test, try everything out in the lab. We have an SEM, we had did compression testing and all kinds of other, it was a fun class. Anyway, I hope I get to the point where we do the peak identification, we fit the peak, Same thing we did in a fast way, right? And there's a function, we fit that. That is an SEM, the escape peak. This is actually fluorescence, but fluorescence from the detector itself, right? So if you have a very strong peak, you get that. Now we come to the composition. The key thing is that the composition is, as we said earlier, directly related to the number of atoms, linear dependent. If it would not be linearly dependent, we would be in big doo-doo, right? But that makes our life easy because we know that all our intensities are linearly dependent. The number of atoms are actually here, right? So in the relative composition here, we have different losses. We have a backscattered loss, so not all the electrons are really contributing, blah, blah, blah. So we have that, and so where we want to be, where's my K vector? Castaigne? Must be in the next one. So depending on the number of electrons and then some kind of probability factor. And the K factor for relative composition. So you put all the complications. So Castaigne's assumption was if you have the same number of electrons and you put it on pure iron and then you put it on pure manganese, from the difference you can, for your detector system, you can completely calibrate the iron to manganese ratio, and then you put oxygen in there. That's a bit more difficult, but then you use manganese oxide for something that you really know. And so the way to get around it is to do that for a reference one. So we use a reference here, and you see everything that's complicated and unknown is in here. So we just make, and you get this calibration specimens. You can buy them from NIST. And they have very, very well-controlled compositions. You can be cheap if you have a high TC superconductor that you know is superconducting, right? Then you know exactly the composition because, BIPCO or whatever, BISCO, these compositions are very, very well defined, and then you know that the property is superconductivity. So if it's a good superconductor, you know your composition, and you just use that. Other materials as well, so you can use very clean aluminum. If you have a good furnace, you mix a few of them together, and you can do that too. So some compounds, if they're ordered, you know exactly what their composition is. So these kind of samples is what you're after, and then you can calibrate your system with that. And it depends on what kind of sample you have. You can get extremely good at that. You can actually, it has been shown that it's parts per million can be quantified if you do a very good quantification with even an EDS detector. You don't have to go to the atom, also to wavelengths dispersive X-ray spectroscopy. You can do that with a good EDS detector nowadays as well. And of course, in the electron microscope, you can do that quantitatively. So the best calibration is always for EDS, because there are so many different pathways. This atom can relax and send out a photon from that. The best one is always using calibration samples for standard. And then you have to be in an SEM much more careful, because topography can get you, right? So we need to know the path within the sample. If you have a big mountain between where you generate the photons and where the detector is, then obviously you will have a lot of absorption there. So sample geometry and the quantification. So what is not known? Ionization cross-section is relatively well known, but because you have so many factors, it's an error propagation. So you have small errors here. You get, as you go with different multiplications, the errors will multiply as well. I always use the example of computer chip production. So you can see I taught the device fabrication, or material science of device fabrication for some time. And so you have these different steps in the device fabrication. And if you can reduce it by one step, your yield goes up by 1%, probably independent of the how good your step was. Even with 99.99, and we calculate that it's about 1% that you gain if you can leave that out or can combine steps, and you have the same failure rate. So we don't know the fluorescent yield very accurately. Could probably be measured better. Atomic weight. So we don't know exactly the absorptions, but we do that iteratively anyway. Detector efficiencies and the relative transition probabilities are the key factors that change and are not really known that well. So everything we don't know very well, especially the fluorescent yield with the different pathways that can be happening, is a key thing that is not known. And so what you do is you establish that for your system with your angles and everything experimentally, and that is at this point in accurate way of doing that. The references, as I said, usually it is silicon or iron. If I remember right, in our microscope it is silicon. Iron would have the advantage that it is in the middle of the of most spectra, the energy scale of most spectra. And then if you want to have the difference between two, we always use the right? Ka over Kb, then we have Ka over K silicon, Kb over K silicon, so the silicon falls out and we can use it as a reference for two materials, relative intensity. Okay, that's it from me. We are till lunchtime. Let's see if they have more questions here. Huh? Yeah, no chocolate today. Sorry. The mean free path in eels, so you can measure the thickness. The mean free path in eels is usually, we will discuss that, is usually not very accurate. I would suggest convergent beam patterns in two-beam condition. So thickness fringes there can be directly correlated with the crystalline part of that. So if you have a good sample, that gives you an excellent one. Or you can do, say, absolute thickness with the ionization edges. That works also very well, and we'll see how that works at 3 p.m. when we do the yields. Local composition can be, as I said, so most of the samples, relative sample thickness can be quite illuminating. So if you have something that you know directly next to it and the compositions, then you can actually infer the composition, the thickness quite accurately, right? So, or you calibrate the inelastic mean-free path for your spectrometer conditions, which means your effective collection angle.